Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the class of CS103 Computer Programming. This is lecture 1, where I'll be introducing you to the concept of what a computer programming really is. And I'll show you some examples of typical computer programs. And this will basically be the building block for you for further lectures. So without further ado, let's begin to know what computer programming is. And I think this needs to start off with some of the introduction about myself. I was a graduate. I am a graduate of GIK Institute itself, and I graduated from GIK back in 2006, and after completing my bachelor's. So I actually started my bachelor's in 2002, August 24, if I remember the date correctly. And the first 4 months were spent doing a very similar course called CS101, which was my first computer science or programming course as such. And I didn't have any background whatsoever about computer programming or even computers itself before that. And I think this generation that I see here now among yourselves, this is much more aware of computer programming and about similar, technologies like mobiles, like smartphones, like tabs. They are much more aware than at least what I was back in 2002. And I assume, or I'm pretty hopeful that, or pretty positive, I must say, that you guys are going to, you guys and girls, sorry, would be doing an excellent job in learning programming and about knowing it. So any kind of confusion, if you are nervous or if you feel uncomfortable in doing programming, you should allay those fears straight away, because here are a couple of facts about you or your peers around. At least 2/3 of AI, CE, and CS students will not have taken any formal CS subject course before. So, and that is my assumption, and that is quite true for most of you. So you should, even if you don't know, well, it should give you a bit of a satisfaction that 2/3 of you, or a vast majority of you, have no information about this as well. And that means that every one of you is learning from the very basic start. What is important for you and what matters ultimately for everyone in this course is that it is not how much where you stand or relative to your classmates. It, of course, it does in terms of your grade, maybe. Um, but what I'll try to do is that if someone knows programming, he should get a good programming grade. And at the same time, if someone does not know programming, he should never get a good grade. So he might even fail the course. This is so important. And hence, what is important for you is that if you're doing well, if you're learning the concepts well, if you are, after 4 months, if you evaluate yourself and you are way better than where you started, I think the ultimate aim of delivering this course is done for me. And that is my aim, to improve you in your relative to your learning process. So what is computer science? Computer science is basically defined as nothing but fundamentally problem solving using some kind of computing tasks. If you talk about problem solving, it is a process of taking some input and generating your output or some output from this particular input. The in-between process which you use to convert an input to an output is called computer science. That is the computing part that you need to perform. What we need to do is, of course, if you want to process it, you need some way to represent the input. You need to store the input. You can work on the input then, and then basically produce an output standard format as well. So these are some of the tasks that you need to do in order to convert your program from um, input to output. So what is computer science? A computer science at the or computer at the lowest level, if you go to the very basics of it, and you probably have studied it in the course Fundamentals of Computing already, is basically storing the data in binary, which is a numeral system in which there are only two digits, 0 and 1. So every information, every single process, every single processing is being done on a data. That data is being stored in binary. So what is the data here? The data can be music, so it's a sound. It can be a video, like the one you're seeing here. And again, video has to be represented in zeros and ones. It can be text. The text is also represented as zeros and ones, and so on. So any kind of data, anything that you may call as data, will be stored in your computer in the digital format. The digital format is binary, which is 0 and 1. So what is a binary system? A binary system is very simple. So when we started to learn to count, we basically used our 10 fingers. So one finger represented one number, one digit. Second number basically represented two digits, and so on. So basically, if you use all your 10 fingers, counting from 0 to 9, you can basically use the decimal system. Deci means 10. So if you're using all your 10 fingers, using a decimal system and using just one finger, that one finger is basically unary system. For example, 123, 123 is represented, it represents 123 to the base 10 or in the decimal system. The 3 is in the ones column, the 2 is in the tens column, and the 1 is in the hundreds column. So 123 can be represented as 100 into 1 plus 10 into 2 plus 1 into 3, which is 100 plus 20 plus 3, which is again 123. So this is something that you're already done and you already know about it. So I won't go into too much detail. Each place for a digit represents a power of 10. Since there are 10 possible digits for each place, hence you can basically represent various values. In binary, which is just two digits, we have the powers uh, of 2 for each place value. So 4, 2, 1, and 0. So for example, 0, 0 would represent 0. But if we change the binary value to say 0, 1, 1, the decimal value would be 3 into 4 plus 2 into 1 plus 0 into 1. And then if you want to represent it into 8, similarly the powers would then be 8, 4, 2, 1, and 1. So binary makes sense for computers because we have power. We can power them with electricity, which can either be on or off, so that each bit only needs to be on or off. So you can store them in a certain state. That state represents 0 or 1 being on or off. So typically in a computer, there are millions or even billions of switches called transistors that can store electricity and represent a bit by being on or off. With enough bits or binary digits, computers can count to basically almost any number. But typically what you need to know is that 8 bits make up 1 byte. So 1 byte is basically 8 bits stored together. And those bits can have possibly values from all zeros to all ones. To represent all letters in a data, we need to decide which number maps to which letter. So there's only that mapping that goes on. And that mapping was actually decided many years ago collectively on a standard mapping, which we now called ASCII. ASCII is basically just a mapping, it's nothing else. So in ASCII, what we've done is we've mapped some letters to some numbers. Those numbers are of course stored in binary, but since binary is very hard for us humans to read, so it is done, the numbers are shown here in decimal, but they are going to be stored, you need to remember, in binary and retrieved in binary as well, and then they can be interpreted into whatever letter they map to using the ASCII table. So for example, the capital letter A maps to the number 65, the capital letter B maps to 66, and so on. The ASCII mapping is also applicable on different kinds of punctuations and other symbols as well. Similarly, other characters that cannot be mapped through ASCII are part of what we call Unicode. And Unicode basically uses more bits than ASCII to accommodate all these other characters as well. So those letters that have accent marks and emojicons, etc., are part of Unicode, but not part of ASCII. So whenever you receive an emojicon, or computer is actually just receiving a decimal number, for example 128514, or if you can read binary, here's the binary number for 128514, and this is then mapped onto the image of the emoji and displayed out as that particular image. So each image itself, as well as the text, etc., can be represented as Unicode or ASCII characters. How do you represent data? Well, an image too is comprised of many small square dots of pixels. Each pixel has definitely got a color, which is colored using a system called RGB, red, green values, red, green, blue values. So red, green, blue values are basically stored. So you now have got 3 different values for each color. For example, by mixing these together, these different colors, you can come up with millions of colors. So for example, red, green, and blue values given here, 72, 73, and 33, are combined together to get a shade of a yellow color, and that shade of yellow color can be seen in the emojicon if we zoom in far enough. Then here's the problem of how you represent data. The computer programs know, based on the context of its code, whether the binary numbers that are displayed or that are transferred are basically to be interpreted as a number or letter or pixel values. And if we talk about videos, videos are just many images that are displayed one after another at some number of frames per second at a particular speed. Similarly, like I said, music too can be represented by the notes being played, by the duration, and by their volume. So, what is an algorithm? An algorithm is basically the black box that we called uh, that converts from input to output. And what we learned so far is we can now represent inputs, which is your music or video or text or whatever, in ASCII or Unicode format, and you know how to do it. Or if it's an image, you can, or a video, which is just many images stitched together running at a particular frame rate. For example, AVI videos run at a frame rate of typically of 30 images per second, and that is the way we are now comfortable enough, I think, to represent any kind of input and output, be it text or video or sound. But how do we convert an input to an output? And we had basically said that there's a black box, a processing box there. That processing box, or that black box, is a group of algorithms. And what is an algorithm? An algorithm is nothing but a step-by-step introduction to solve, or step-by-step instruction to solve a problem. This is something that you'll hear here, and you probably keep on hearing in a lot of other courses as well, like the discrete structures and in data structures course as well as in maybe in object-oriented programming. But this is something that should be ingrained into you. An algorithm is nothing but a step-by-step instruction for solving a given problem. Step-by-step instruction for solving a problem. Step-by-step instruction for solving a problem. This should be ingrained into your mind. What is an algorithm? A step-by-step instruction for solving a problem. So let's say that we wanted to find a friend called Hashim Ali in a phone book. How do you solve it? Uh, well, here's a simple thing. You go and open your phone book, start from the first page, from one page at a time, and on each page check the entries that are there, the names that are there, until you find either the person Hashim Ali in the book, Or, well, you go through the whole book and you cannot find this person Hashim Ali in the phone book. But here is the problem. uh, if you go through the whole book one page at a time, this is going to be a really slow process. It's, for example, if your book is, let's say, 1000 pages, and you take and you're really fast and you take, let's say, 1 minute to process through all the names on the pages that are open. Think about it. For 1000 pages, which are 500 page flaps that you need to do, and that will take you 500 minutes to go through all the 500 pages to identify that this person, Mr. Hashim Ali, is not in the phone book, in the worst case scenario. And 500 minutes is a lot of time. Well, the simplest way is you can halve this time by flipping two pages at the same time. So instead of flipping one page, you actually flip two direct pages. So this is going to be um, this is going to take you 250 minutes, halving this time, and so on. But there is one problem. The problem is that if you flip the page on which this person, Mr. Hashim Ali, was, mentioned, you're going to probably miss your solution. The solution is there, but you have missed him. Um, can there be a more efficient solution? Well, there is one particular characteristic of the phone book that we can take advantage of. Let us suppose that the phone book is basically sorted on the alphabetically based on the name of the person. So if, for example, the person that I'm searching for is named Abdul Razak, and the other person that I want to find, or let's say, if I open the book and the last name on the page is Abdul Razak, and I want to find Hashim Ali is going to be situated in the later pages and cannot be before the person Abdul Razak. So clearly, or on the pages on where Abdul Razak is situated, on the pages before Abdul Razak. Hence, we know that if I have the person Hashim Ali is on the next page or in the next few pages, but definitely not before it. And that particular characteristic can be used as an advantage. How? Well, what we need to do is we need to open the book at the half in the middle. If the last person in the middle is basically greater than the alphabet is larger than H. So for example, let's say I, J, K, or whatever. We basically know that we need to go on the previous page or the previous part. And that's where we can be sure to find Hashim, or we are sure to know that Hashim does not exist in the whole book. By this particular process, we actually have, if you open the middle, you have actually thrown half of the book away. If Hashim is basically, if H is basically in the later part, what we need to do is we need to throw the first half and keep the second half and search again. So what, in each step, we can divide it into two parts by opening in the middle each time. And based on the the value in the middle, we can decide if we have to go look into the left half or on the right half. So if you want to start with 1024 pages, for example, we'll only need 10 steps of dividing in half before we finally have got just one page remaining where we can check for this person Hashim Ali, or verify that he does not exist in the book directly. This is an algorithm. And in fact, this particular part can be represented by what we call efficiency of each of these algorithms. And this can be represented by using different charts. So for example, the part which we use now was log 2 to the base n, the most efficient part. The one where we looked at each page was this straight line n. So for 1024 pages, we would need to look at all 1024 pages before we are able to decide that this person Hashim Ali does not exist in the book. For this part, where we looked at two pages simultaneously or skip two pages, this is the line that displays that solution, and this is the line that displays the solution where we divide into middle and then look at each half only. Our first solution, it was the red line here. Like I said, it solves the problem linearly. And you can see this is linear line. The second solution, 2 pages at a time, is also like the yellow line. It is, the slope is less steep, but still it is still linear, as you can see. For log n, well, that is logarithmic, since our time to solve rises more and more slowly as the size of the problem. Size of the problem is continuously increasing, but this increase in the time to solve is kind of logarithmic. So in other words, if the phone book now goes from 2000 to 2000 pages, we only require one more step to find Hashim. If the size doubled again from 2000 to 4000, we would still only need one further step. But in case of linear, from if we increase from 1000 to 200 books, the number of steps will also increase from 1000 to 2000. In case of n by 2, it is going to increase from 500 to 1000, a linear increase. But in case of the logarithmic, you see a linear increase does not result in a linear increase in the logarithmic function, but rather a logarithmic increase. So what is a pseudocode? Well, pseudocode is nothing but an informal syntax to write a more specific version of English or any other human language that represents our algorithm. The algorithms are going to be represented by pseudocode. What is our pseudocode? Well, the pseudocode for the problem that we mentioned in this algorithm is that we pick up the phone book, we open the middle of the phone book, we look at the page. If Hashim is on this page, we just need to call Hashim and we are done, right? Otherwise, if Hashim is not on the page, then check where Hashim is. If Hashim is earlier in the book, then open to the middle of left half, because Hashim is earlier, open the middle of left half, and then try to go back at line 3 and continue. Otherwise, if Hashim is not earlier in the book, then of course Hashim is late in the book, right? Most probably. In that case, open to the middle of right half of book and go back to line 3. But let's suppose that Hashim is neither in the earlier half nor in the later half, and is supposed to be on the page but is not on the page as well. In that case, use the else statement here, which basically says that this thing verifies that all the previous conditions that we have mentioned here are false. Hashim is neither on the page, neither on the left side, neither on the right side. That means Hashim is not present. Simply quit the program. This representation here is what we call pseudocode. So if you look at the pseudocode, I can come up with some of the things here. Some of these lines start up, as you can notice, start up with a verb or action. For example, pick up, open to, look at, call, open to, quit. These are all what we call functions. In the second part, you also have got some kind of branching options that are different parts. For example, if we find Hashim on a page, we just call him and we are done. We don't need to talk about earlier in the book, later in the book, or do anything else, right? We have found Hashim and we are done. So this is one path that we can take. Another path that is possible is that where Hashim is not on the page, and then in that case, we need to verify if he is present in the earlier part or in the later part or not present at all. And only then will we take the second, third, or fourth path, whatever it is. But remember, these are like forks in the road. So the forks here are basically, you can only take one path. You cannot take both, or you cannot come back to and change your path midway. It's basically, if you choose a path, you've chosen it. So these paths or these branches are what we call conditions. Things that are either met or not met. If they're met, they're updated. If they're not met, well, we don't take that particular condition. Okay. The questions that decide where we go are called Boolean expressions. And what are Boolean expressions? Well, they're basically conditions that are either true or false. And these conditions that we showed earlier are based on these Boolean expressions. So for example, Hashim is on page, this is a Boolean expression. Hashim is earlier in book, or Hashim is later in the book. These are all Boolean expressions. If they are true, you execute them. If they're false, we cannot execute them. We move on to the next Boolean expression, evaluate it, and move on and on. So if all these three are false, this one is always going to be true, regardless. And then there are other things, other words that are leading like to cycles. For example, go back to line 3 commands here. I'm actually making you go back, and you can actually be stuck in a cycle or continue in a cycle. These cycles are what we call loops in programs. So now what I want you to do is I want you to go into a programming language called Scratch. It contains these building blocks that we've just discovered: functions, conditions, Boolean expressions, loops. We'll use a graphical programming language which is called Scratch. You can just, Google it and use Scratch language to drag and drop blocks that contain instructions. Later on in our course, we'll move on to textual representation programming languages like C and Python and JavaScript. We'll be moving on to C++ for examples here and for this course, but of course you can apply the same concept onto Python and JavaScript. All of these languages, including Scratch, have more powerful features like variables, threads, events, and so on. What is a variable? The ability to store values and change them. What is a thread? The ability for a program to do multiple things at once. What is an event? The ability to respond to changes in our program or inputs. So whenever an event occurs, we should be able to respond to it as desired by us. The programming environment for Scratch looks something like this. So you can go on, you can search the programming language. You can just write Scratch MIT programming language, and you'll come to this interface on the website. And I think that's pretty much it about the lecture 1. I'll highly recommend you to go and watch CS50 course on the first lecture for getting a more informed approach to Scratch and about algorithms and about pseudocode, etc. by David Melan. I think the course is available as CS50. It's a course offered by Harvard University professor David J. Melan, who is very energetic, and you'll probably love his lectures. But he delivers an excellent intro about these things, and you can probably go and watch some of examples on Scratch as well on the website on the YouTube, and I think it will be extremely helpful for you. So in the next lecture, we'll now start with the book itself and C++ programming, and I hope you have kind of learned something about Scratch from me in this course and about basics of programming in this lecture. In the next lecture, let's talk about the C++ as a programming language and the different syntax and other things about C++. That is, I think, the chapter 1 of the book, Devendra S. Malik book. And with that, I'd like to thank you all for your time. Take care. Allah Hafiz.